Hello everyone, welcome back. Today we are diving into BoT-SORT, a famous tracking algorithm for multiple object tracking in video sequence. If you ever worked with surveillance footage, autonomous driving data, or crowd data, you know how tricky it can be to keep track of individual, especially when people overlap, cameras move, or the scene get clustered. BoT-SORT tackles all of these challenges head-on, making your tracking more accurate and reliable. So imagine a situation where you have a video of a busy street and people keep crossing each other. Traditional trackers like SORT or DeepSORT can lose track of who is who when the people walk behind each other. That's called occlusion, or when one object blocks another object. Plus, if you have a camera which is moving away, say it will be a drone or a handheld camera, so throw off the motion model. BoT-SORT solve this issue by combining smart motion prediction, appearance feature, and a technique called camera motion compensation, which stabilize your video so the tracker see only the object moving, not the whole scene. So, before moving into its implementation, let's review its research paper. BoT-SORT research paper focuses on multiple object tracking, specifically developing an advanced tracking by detection system for the object tracking in video sequences. Multiple object tracking, or MOT, is the challenge of detecting and tracking all objects in a scene while maintaining unique identifier for each object throughout their trajectories. This technology is absolutely fundamental for applications like autonomous driving, video surveillance, and traffic monitoring system. Uh, Previously, the problem authors were facing is stated here is the author identifies several critical limitations that were plagued existing sort like tracking algorithm. First, there were serious Kalman filter state vector issues, like most existing method uses deep sort approach of estimating aspect ratio instead of direct width estimation. This led to inaccuracy in bounding box dimension and suboptimal localization essentially. So the tracking boxes did not fit the object properly. Second, the camera motion sensitivity was a major problem. IOU-based tracking approach heavily relied on predicted bounding box quality, which failed dramatically in dynamic camera scenarios. Like when camera move, it causes significant shift in bounding boxes location, resulting in low overlap between predicted and detected boxes. This ultimately led to increased ID switches and false negative, meaning objects would lose their identities or disappear entirely from tracking. Third is there was a fundamental existing system trade-off, we have to choose between accuracy and identity preservation. Using IOU typically achieve better MOT, which is a metric for multiple object tracking, while re-identification approaches achieve higher IDF one metric, but you could not have both at the same time. So it was a trade-off situation between accuracy and identity preservation. So author introduced a novel approach. The author developed BoT-SORT and BoT-SORT re-identification with three groundbreaking innovations. First, it introduced enhanced Kalman filter, like they completely redesigned the state vector to directly estimate width and height using the format instead of the aspect ratio. This provides much more accurate bounding box prediction that actually fit the object being tracked. Second one is camera motion compensation, or CMC. This they implemented a conventional image registration using enhanced correlation coefficient from to correct the camera motion. This make the tracker robust to dynamic camera scenarios. like if the camera is tilted or moving in another angle uh, in every frame. So this module would handle these cases so the tracking identities don't switch and be preserved. Third is it introduced a novel IOU re-identification fusion. Instead of traditional weighted sum approach that other method use, they developed a completely new method. They rejected low similarity candidates and uses the minimum between IOU distance and adjusted cosine distance. This clever fusion strategy is what allows them to achieve high performance in both motion and appearance tracking. So, how the new method fix previous problem? For improved bounding box accuracy, the direct width height estimation in their enhanced Kalman filter produce significantly more accurate bounding boxes. They actually show this visually in figure 3. Let me show. Like you can see this of their paper. This difference is quite striking. For camera motion robustness, CMC module accounts for rigid camera movement by estimating background motion and correcting Kalman filter prediction accordingly. This dramatically reduces uh, ID switches scenarios, solving one of the biggest practical problems in real world tracking. For unified performance, their IOU and re-identification fusion method combines motion and appearance information, achieving high uh, performance in both MOTA metrics and IDF1 metrics. So, we have all talked about its benefits, but there are some limitation also, like computational overhead. Camera motion calculation can be time consuming for large image. Through the author note this negligible compared to detector inference time in most practical scenarios. There is also the issue of scene dependencies, like in a scene where high density of dynamic objects, camera motion estimation may fail due to insufficient background key point for reliable estimation. Like if I am tracking an object in a wall, so there is not much information to get what this frame orientation is. So tracking may fall here. So there is also a problem of motion estimation failures, like incorrect camera motion estimation can lead to unexpected tracker behavior in complex scenarios, creating a potential single point of failure. So in my approach, while the technical contribution are solid and the performance are impressive, the system's complexity may limit adoption in production environment. Whereas the approach feels like an incremental but much more significant improvement rather than a paradigm shift, which is actually appropriate for a mature like object tracking. Uh, because in object tracking there are various other algorithms which are better like byte track, for example. So there you have it, a comprehensive breakdown of BOT, a sort revolutionary approach to multiple object tracking. We have seen how they tackle the fundamental problem in a tracking system. Uh, Now let's move to its code implementation to see how you can perform it on your own and start tracking object. Now let's see how you can implement BoT-SORT. In this notebook, I will tell you two ways you can perform BoT-SORT. First is using Ultralytics, as its default tracking algorithm is BoT-SORT, and second one is using PyPI library of BoxMod. It's a Python library you can use to implement various tracking algorithm. So it also you can be used in implementing BoT-SORT. So let's start by see- seeing our Python version. I'm using Python 3.10. Now let's install the required libraries there, which is BoT-SORT and Ultralytics. These are the version I am using here. So let's run this helper function. This helper function is used in displaying the sample video I'm going to uh, use in this tutorial. Like there are various videos I am going to use. So I have created this function for better visualization. Now let's run this function. Now let's see the our first sample video. This is the sample video I'm going to use first. This is a sample video containing various objects which are people here, and they are going in various direction. The total count of people is very hard to see, so let's see how our tracking algorithm perform here. So for I'm using Ultralytics first. So to track using Ultralytics, you just have to import YOLO from Ultralytics and provide the model name to YOLO. As you can see, I'm using YOLO 12x, and to perform tracking, we just have to use its track function, provide the address image video part, and then truly persistent for videos, and also input the target classes. Now run this code. As you see the inference result of BoT-SORT tracking, it has failed to detect some objects in this scene. This was happened due to the YOLO 12x limitation in object tracking, but the tracking trajectories were clear and there were no identity switches in the video. Now let's move to another video. Here I'm using PyPI method. So let's. This is the sample video I am going to use. This is a video where there is a camera movement. It's not very much and you can see, but the camera is moving. So it's a good video where you can see how BoT-SORT works. So to use BoT-SORT using BoT-SORT, we just have to provide with this command line. So we have to just provide a BoT-SORT track source and paths to video, then provide the tracking method, which is the algorithm I'm going to use. Here it is BoT-SORT, and then the YOLO model, which I'm going to use, then the re-identification model I'm going to use, then the target classes. So let's run this code. As you see the result here, you see the inference was good and the tracking method were perfectly implemented, as there were no identity switches and object detection was happening quite good, so there was no object left behind. Now let's take another example where we detect car. This is the sample image I'm going to use for our next tracking. Here you can see this is a video of a highway where multiple cars are going forward. This is a very hard image to track as the objects are getting smaller with each frame. Now let's see the inference result of tracking of BoT-SORT here. So overall the tracking was very much good, but there were some frames where objects were not detected even if they were present. So the tracking algorithm doesn't identity switches it, so it was a good tracking implementation. Now let's track athlete. This is a sample image of athlete running on a track. As you can see, this is a very sample sports video, which is very good for tracking algorithm to be tested. Now let's see how BoT-SORT works. So the tracking algorithm works greatly here. The tracking was perfect. There were no identity switches and there were no frames where there were no object detected. So it was a great example for BoT-SORT implementation where it worked perfectly. But there are will be a limitation. We will see it further. Let's test another BoT-SORT on another video of a plane, or else we can say multiple planes. This is a sample video I'm going to use to track uh, plane using BoT-SORT. As you can see, these plane are following a curve path, and it's these objects are first come from small pixel to larger pixel. So let's see how BoT-SORT track these objects. BoT-SORT work here very much great or perfectly, you can say. There were no identity switches and tracking was very much smooth. Object detection was very much perfect. But these are all the benefits of BoT-SORT. Let's see the limitation of BoT-SORT in this video I'm going to use. Let's track some birds using BoT-SORT. This is a sample image of birds flying across sky or above the ocean. You can whatever you can see. But in this image video, you will see there is some tracking issue which will be faced by uh, BoT-SORT. Let's see its inference on this video. As you seen in the tracking inference of BoT-SORT, there was various issue with tracking like the identity switches or object detection failure and many things. So there is a clear limitation of BoT-SORT due to its dependency on object tracking, which is a significant limiter for its trajectory tracking. So with this, our tutorial on BoT-SORT is over.
For more on machine learning, you can check our GitHub, where you will find various material like notebook, blogs, and videos. Check it now